last class we were working on interpolating a set of data points, and this class we're going to continue working on interpolating a set of data points. But the difference is the following. In the last class, we interpolated a set of data points with a single polynomial that passed through all the data points. In this class, we're going to interpolate a set of data points with a set, what's called a piecewise set of polynomials to interpolate the data points. So maybe an example would help. So supposing you had 100 data points, some data set containing 100 data points. In the Lagrange interpolation, we would need a polynomial of that order to interpolate those 100 data points. So it'd be one huge polynomial. In today's interpolation, which is called piecewise spline interpolation, we would just interpolate using, say, we could use a quadratic function, we could use a cubic function, but we'd use many quadratics, many cubics that would interpolate the data, adjacent data points, and we would join that together to interpolate the entire set of data points. So it's a very different method, it's a very different scheme. The spline has the advantage that it reduces interpolation uncertainties, interpolation errors. When you have large polynomials that you're interpolating with, you tend to get oscillations of the function that you're interpolating with. You especially get oscillations of the function that you're interpolating with near the ends, the bookends of the range of data. You especially get those oscillations of your interpolating function if you have equally spaced equidistant points. So the spline is much less sensitive, much more immune to that particular problem. The complication of the spline is that it's a more complicated procedure. It's a more mathematical procedure to interpolate with many, say, cubic functions or many quadratic functions over small ranges of the data, rather than to interpolate with just one big polynomial over the entire range of the data. Probably that makes sense intuitively, that the spline would be more mathematically complicated. The single polynomial will be more mathematically more simple. Okay, so let me just say a few more words about the interpolation. As I say, a spline is really a set of polynomials that we're interpolating with between data points, rather than a single polynomial that we're interpolating with using to interpolate all the data points. So in the spline, you've got low order polynomials. In the Lagrange interpolator, you've got high order polynomials. So let me give you this example of, say, supposing you had 10 points. So you'd need a 10 order polynomial for the Lagrange interpolation. But if you were interpolating 10 points with the spline, you just need 9 separate low-order polynomials to interpolate between adjacent pairs of points. So if you've got 10 points, there'd be 9 regions that you would interpolate with their own, say, cubic functions. So in this sketch here, no, more than a sketch, it actually is an interpolation. In this interpolation here, between these data points that are indicated in magenta here, so there's 10 data points, I've found the interpolating single polynomial, so the 10th order polynomial, that's in in blue here from the Lagrange method. And then I found an interpolating cubic spline from the spline method that's in green here. And you see that over much of the range, the high order single high order polynomial and the low order piecewise splines both pass through the data points in a similar way. But at the bookend, so this left bookend over here, this right bookend over here, you see this problem of high order polynomials that you get oscillations near the extreme left, extreme right, near the two bookends, that those large oscillations give you large interpolation errors, large interpolation uncertainties. So this was discovered by sort of mathematician Runge, that we've met that name before, it was an important discovery because up to then the high order polynomials was the preferred method of interpolating data because it was mathematically more straightforward. But it meant that for large data sets, you really want to use splines, although it's more mathematically complicated, it's more accurate. So it's interesting that the credit of invention of splines is given really to General Motors, because splines are important in the design of, say, car bodies or aircraft bodies. And the first splines were physical splines rather than computational splines. So they were literally like pieces of wood or pieces of flexible material that you could bend around a series of points and in that way physically interpolate rather than mathematically or computationally interpolate. So that's the origin of the spline. And I believe spline, the S in the spline is for a smooth function. The P in spline is for this piecewise, you know, a collection of many cubics or many quadratics. And then SP line is the spline. Okay. So let's take a look at a particular spline now, rather than just general splines. So we're going to look at cubic splines, where between each pair of adjacent data points, we're going to interpolate with a cubic spline between each of these pairs of data points. So in this little sketch here, the same sketch as I used in the last class, basically, we got a series of data points. So X is the independent variable, Y is the dependent variable, and the subscripts label the various data points. So we got N data points here. And we are going to interpolate with this blue function here, using this piecewise spline, where between each pair of data points, say between X1 and X2, we're going to represent that interpolation as just a cubic function. And then between, you know, X2 and X3, we're going to interpolate that region with another cubic function. And then between X3 and X4, yet again, another cubic function to interpolate. And so between each adjacent pair of data points, we're going to interpolate with this particular function here. So there's a cubic term with some coefficient, there's a squared term, some coefficient, a linear term with some coefficient, and a constant term. So there's 4 parameters, 4 coefficients for each of these cubics between each of these regions between pairs of points. If you think about it, if you've got n points, you've got n-1 little regions between adjacent points. And so you're going to have 4 times n-1 coefficients for the cubic spline. And so we've got to determine 4 times n minus 1 coefficients if we're going to accomplish this cubic spline. So that's quite different from the case of the Lagrange polynomial interpretation, because in the Lagrange polynomial interpretation, we just had the number of coefficients just match the number of data points, basically. So the question then becomes, the problem then becomes, well, how am I going to determine these 4 times n minus 1 parameters of my piecewise cubic spline? So we need to set up a number of constraints that together will determine those 4 times n minus 1 coefficients of the piecewise cubic spline. And so these constraints are listed over here on the left-hand side. There are basically 3 categories of constraints. So I split them out into these three pieces here. So if we start upstairs here, maybe it's helpful to imagine, say, this first point and this second point, and this cubic spline between those 2 points, this cubic polynomial between those 2 points. The first constraint basically says that that line has to go through the point on the far left, so point number 1. It has to go through the point on the right, so point number 2. So the spline in that region has to intersect with those 2 points. And so one pair of constraints on this particular spline here between the first 2 points is that polynomial, remember we called it S, that has to be equal to y1 at x1, has to be equal to y2 at x2. So that's one requirement. The spline, in the language of splines, the spline must intersect with the knots at either end of the spline. And so that's 2 constraints, but that's 2 constraints for every cubic function. And we remember we've got n minus 1 cubic functions across the range of data. So this is 2 constraints for every one of the n minus 1 functions. So it's 2 times n minus 1 constraints come out of this guy here. Okay, second category of constraint. Second category of constraint is that at the knots, which is where one cubic function is joining with another cubic function, we want those cubic functions to join smoothly. And joining smoothly here means that the slopes are the same for this spline on the left and this spline on the right at that knot. And that the curvatures, so the rate of changes of the slopes, are the same for this at this knot here, for this cubic function and this cubic function. So that there's 2 constraints here at each knot. One is that the slope of the spline of the cubic function, say on the left, and the slope of the cubic function, say on the right, are the same. So that's this top constraint here. The primes indicate slopes, and the I and the I plus 1 indicate is the function on the left or the right of the knot. And then this second equation here is that the curvatures are the same. The rate of change of the slopes are the same. So the double prime is indicating this is curvature, second order differential, and the I and the I plus 1 is this is the function on the left and this is a function on the right of the knot. So out of this, there's 2 constraints there I've listed for the slope and the curvature, but those constraints apply to every knot other than the bookends on the far left and the far right. So there are n minus 2 knots in between the bookends, because there's n data in total. So there's n minus 2 bookends in the internal region, and so we got 2 times n minus 2 constraints from requiring the slope and the curvature be smooth. There's two final constraints, and there are choices you can actually make about these constraints. I'm going to discuss one of the choices that's a common choice, but there are actually other ways of defining these constraints. One common way of obtaining the last two constraints, and it concerns the bookends on the far left and the far right, is to say that the curvature of your function on the far left and the far right is going to be zero. You're going to just define, because you don't know what's beyond the far left. You don't know what's beyond the far right. Let's just define the curvature there to be zero. It's sort of an unbiased kind of assumption about what's going on to the far left and far right. You can't see to the far left. You can't see to the far right. So don't assume that it's going to curve up or curve down. It's just going to continue in the direction it was going at the bookends, at the endpoints. So that's two more constraints, and it's only two constraints. It's that the slope of this far left cubic function is zero at this point, at the far left point, and the slope of this far right cubic function is zero at this far right point. So that's this equation here. So that's two constraints. So if you now total up all these constraints, we've got 2 times n minus 1 from the fact that the functions must intersect the points. We got 2 times n minus 2 from the fact that at the knots, the slopes and the curvatures of the joining functions must be the same. And then we got the bookend constraints, 2 of those. And if you add this up, this is 4 times n minus 1 constraints, which is exactly what you need. So we've got, if in our cubic splines, we've got 4 n minus 1 parameters, coefficients, and now we've listed 4 times n minus 1 constraints on those parameters. And so this is a problem like equivalent to 2 equations, 2 unknowns. You can solve those 2 equations for those 2 unknowns. Of course, we've got here more complicated situation where we got many more equations, many more unknowns. And the number of equations is going to depend on the number of data points. So let's look at a simple example. First simple kind of non-trivial example is to have 3 points that you want to interpolate with a piecewise cubic spline. So in this sketch here, I've got these 3 points. The dependent variables are the x1, independent variables, x1, x2, x3, and then the dependent variables are the y1, y2, y3, and here are the values that I picked. And so when we interpolate using a piecewise cubic spline here, what does that mean? It means we're going to have 2 cubic functions. One cubic function in this region on the left between the first and the second data points, and a second cubic function in this region on the right between the second and the third data points. And so I wrote out those 2 cubic functions here. There's S1 for the left-hand cubic function. It's got 4 parameters in it. And S2, it's the cubic function over here on the right-hand side. And it's also got four parameters in it. So there's a total of 8 parameters. And that's just that 4 times n minus 1 is going to be 4 times, we've got 3 points, so it's 4 times 2, which is 8 parameters. So it makes sense. And so we've got to determine those 8 parameters. I labeled them as like A1, B1, C1, D1, and then A2, B2, C2, D2. We've got to determine them from those constraints on intersecting data points, the curvatures and the slopes at the knots, and the bookending. So how does that work in detail? And look, this is where you can see that even for 3 points, this is going to get complicated mathematically. if this was 3 points in a Lagrange polynomial, this would be rather straightforward. But 3 points and piecewise spline interpolation is already getting complicated. You can imagine how complicated it would get with 4, 5, or more points. Okay, so the fact that the cubic function on the left has to intersect this point here and this point in the center here, and the fact that this cubic function on the right has to intersect this point on the right and this one in the center here gives us 4 equations. So that's these 4 equations here. And so these are 4 constraints on the coefficients A's, B's, C's, and D's based on the values of the X's and the Y's. So there's 4 constraints. What about where the 2 cubic functions join? Well, there's only one knot here where they join. It's this point in the center. And at this point in the center, right, the slope of the function on the left must be the same as the slope of the function on the right. Curvature of the function on the left must be the same as the curvature function on the right. So there's 2, we're going to get 2 equations out of this smooth joint at this knot, and they're these 2 equations here. And so all I'm doing to get this equation here upstairs and this equation here downstairs, I'm basically differentiating this cubic function on the left to get the slope, differentiating this cubic function on the right to get the slope. I'm equating those 2 differentials, and I'm equating them at that point, x2, y2. And so in this equation here, you just see the x2s, because that's the knot, that's the location of the knot. The same thing down here for this second equation, right? I'm taking the first differential and then the second differential to get the curvature of this cubic function on the left and this cubic function on the right. Then I'm equating those 2 curvatures for those 2 functions. And when I equate those 2 curvatures, I get this equation here. Again, it only depends on x2, because we're just thinking about matching the curvatures at x2. And so there's only an x2 in this equation here. And then finally, these last 2 equations here. The top one is the second order differential of the polynomial on the left-hand side to get the curvature, and setting that equal to 0. We're saying we want no curvature at this point here. And the second equation in this category is, again, taking this polynomial, taking the second order differential of that, and setting that equal to 0, because we want no curvature of this polynomial at this location either. And so this is basically our 8 equations that provide the 8 constraints to determine the 8 parameters of the 2 cubic functions that we're interpolating these 3 data points with. Okay, so this is a problem of linear algebra. It's an equivalent problem of, as I say, 2 equations, 2 unknowns, but now we've got 8 equations, 8 unknowns. And so it's very handy in linear algebra, very handy in Python if we write this out in matrix form, and then we can solve it in Python in matrix form. So that's all I'm doing here. So upstairs here, if you look at this product of matrix and vectors, this is simply those 8 equations that I wrote down on the last slide. So if I take these this vector here, which is the 8 coefficients of the 2 cubic polynomials in this column vector, if I multiply the top row, I show you I get one of those equations from the previous slide. If I multiply any other row, I get any other of the equations from the last slide. And so this is this sort of summary of those 8 constraints out of which we want to determine these 8 parameters. If I fill in the numbers, so when I go to my Python code to solve these this linear algebra problem, I'm going to have to fill in the numbers for the values of the data points. This is the corresponding problem I have. This is my matrix where I filled in the values of the x coordinates, so x1, x2, x3, x4. This is a column vector where I filled in the values of the y coordinate. Just maybe to make this a little bit clearer, if you imagine taking this vector here and multiplying the top row, that gives you y, this element y1, that gives you this element here. And that was that constraint on the left-hand cubic function must go through the left-hand point. This particular row in the matrix, when you multiply this column vector against this row in the matrix, this element actually gives you the constraint that the slope of the left-hand cubic function and the right-hand cubic function are the same. So that's where this constraint is embedded. And then finally, this one down here, when you multiply this row of the matrix by this column vector here, this is the constraint associated with the fact that the curvature at this left-hand bookend has to be 0. So all of those 8 constraints are built into this matrix. And so you can see using a Python linear algebra and NumPy linear algebra, we've got a matrix problem of this form. Matrix multiplied by this column vector here gives this this column vector B. We know the matrix, and we know the column vector on the right here because they are defined by the data points. And what we want to find is this vector here, because those are the coefficients of the two cubic functions. They will determine the interpolating curve. And so we just want to rearrange this equation here. You can imagine multiplying through by the inverse matrix to get an equation for the column vector that contains the coefficients of the polynomials in terms of that inverse matrix of this matrix here, and the vector B that contain the dependent variables.